Distributivity law of multiplication over plus and plus over multiplication. Algebra is defined on a set of two elements. Okay, again we need two elements. The multiplication operator represents the AND operation, whereas the addition operator represents the OR operation. X plus y is equal to y plus x. Welcome to the next session of Digital Electronics. I am Dr. Soumyashri from Department of Computer Science, Vidhyaashram College. Until this session, I explained you about some of the basic concepts of digital electronics, like what are digital electronics, what are the various concepts of digital electronics, like how does computers are going to handle the numbers or characters or symbols, how you can represent the data in computers using the binary values, how to convert the values from binary to some other system or from some other system to binary, then how to perform the arithmetic operations using binary numbers. How do you perform the complement system? What is the necessity of complement system? And other basic concepts in digital electronics. As I said, it is basic. Okay. Why do you need basic things is to know about advanced things. These are the basic or necessity foundation for learning the different components in digital devices or digital electronic devices, how they are going to use and what are the representation they are going to use. All those things will be the topic of discussion in the upcoming units. Okay. Today, I am going to start in this session with the concepts of second unit. Okay. What does the second unit comprises of is, it consists of the Boolean algebra, some of the basic things of Boolean algebra, how you can use the algebra for binary values or Boolean values like this, and what are the different representation, how do you represent these Boolean values to in the digital components or digital devices. All these things can be discussed in the second unit of digital electronics. First concept in Boolean algebra or second unit is about the Boolean algebra. Okay. Algebra, you know about algebra, isn't it? You have studied algebra in high school, middle school, and you are familiar with the algebraic expressions, like we use x and y like this. We are bringing back that memory once again with the help of the digital electronics. Okay. Here, why do we need algebra and what is algebra is all about is, it is a mathematical system. Algebra can be termed as mathematical system. What does this mathematical system consist of is the set of elements, usually the whole numbers. Set of elements like 1, 2, 3, 4, usually the set of elements or whole numbers, is it not? Along with that, you will be having set of operators, okay, plus, minus, multiplication, division, modulus, like remainder. These kind of operators will be there. There will be some axioms or postulates which are derived on algebra, like axiom of associativity, postulate, distributive, closure, identity, and inverse postulates or axioms or theorems, you can say. You have all these things in an algebra, is it not? We have studied all these things and have forgotten it. Okay, let's brush up all those things once again, but with a new tadka of having Boolean values. Boolean, or what is Boolean algebra then? We have studied general algebra in schools. What is this Boolean algebra is? As I said, the term Boolean refers to only two values. What are those two values? It is either true or false, or you can say on and off, on or off, low or high, 0 or 1. Whenever your expression contains only two values like this, true or false, on and off, low and high, or 0 or 1, any expression, if it contains only two operands or two operands in the expression, it is called as a Boolean. Okay, algebra which uses these two values is called as a Boolean algebra. Okay, what is the necessity of Boolean algebra? Or algebra is defines the rules of calculation, how you are going to calculate the values or calculate the different operations or expressions. Okay, the expressions or the operators with two inputs are usually called as binary operators. Okay, like plus will be a binary operator. Why it is binary operator? You cannot perform addition operation with one value. Can you perform addition operation with one value? You cannot, is it not? You need another operand to perform an addition. This is an operator and this is called as the operand. Which gets operated is called as the operand, and which is going to operate on these operands are called as the operator. Okay, plus is an operator which needs two operands, and they are not restricted to binary numbers, but usually they involve two operands. There are certain operators which handle only one input, like there will be an operand ampersand which operates on only one value, operand of 3, ampersand of 3. These operators will operate on only one operand. They don't need another operand to perform the expression, to execute the expression. That is why the operators which can work on a single operator are called as the unary operators, and which need two operands, minimum of two operands, are called as the binary operator. Okay, involving the algebra which involves the operators and the two binary operators, two operands like true or false, on and off, low or high, and 0 or 1 are called as the Boolean algebra. Okay, there are some of the postulates and theorem that can be used for algebraic structure. They help in formulating the algebraic structure. Okay, some of the postulates can be termed as closure, or simply you can say it as law. Okay, law or theorem, or law or postulate or rule. Okay, one is the closure law, associative law, commutative law, identity law, inverse law, and distributive law. There are 6 different postulates or basic laws that are implemented in the Boolean algebra. Okay, let us have each of these in detail. Okay, the first one is the closure law. What is this closure law is all about is, it specifies that the operands must be close. That means a set, you have a set, if you have a set S, it can be called as a closed set or holds good the closure law with respect to a binary operator, any binary operator, plus, minus, multiplication, division, any operator. A set of S is closed with respect to a binary operator if for every pair of elements of S. So, if S is a set of elements, for every pair of elements in set S, the binary operator specifies a rule for obtaining a unique element of S. So, what in simple terms, what you can say is, a set is said to obtain or said to fulfill the closure law when, if and only if, the operands, when the operator gets operated on the operands, gives a result which again close to S or belongs to S. For example, there are natural numbers 1, 2, 3 up to n numbers is closed with respect to the binary operator plus. You have a binary operator plus 1, 2, 3, set of natural numbers 1, 2, 3 is set to or is closed with respect to plus by the rule of arithmetic addition. That means when you use a plus operator on in this set of natural numbers, it fulfills the closure law. Which one? Plus operator. Because when you perform addition operation on any of 2 elements, every pair of elements, if you perform addition operation on every pair of elements, it will give you the same element, a unique element of S. The result must be unique element of the natural number n. Suppose if I take 2 plus 3, when you apply 2 and 3 are the members of set S. Okay, set S contains set of natural numbers 1, 2, 3. I will take pair of 2 natural numbers 2 and 3 and I will apply plus operator. Okay, so this will give you the result 5, where 5 belongs to same set of natural numbers. Okay, this is what the closure law says. A set S is closed to operator plus only when the binary operator applied on it gives the unique element of S only. The resultant value must belong to same set of operands. Okay. Since for any A, comma B belongs to N, if you take A and B as the operands, A and B belongs to set of N, there is a unique element C which belongs to N. Okay. So, A plus B generates C, operands A and B belongs to set of natural numbers N. The resultant operand will also belong to same set of natural numbers. In such a case, that set of natural numbers is closure to plus operator. Okay, closure to plus operator. But all the binary operators will not hold the closure law good because minus is not close to N. Why it is not close to N? minus operator or subtraction operator is not close to n, because if I take 2 minus 3 as is said in the diagram, which gives the resultant operand minus 1, which is not a member of or not a element of set n. Is it not? Minus 1 is not a element of set n. If I say 4 minus 2, this will become 2. It belongs to set of n, but not all the times the minus operator gives you the operand which belongs to set of n. Okay, you may get element which does not belongs to n. In such a case, subtraction operator is not closure to n. Okay, not closure to n, which does not belongs to n. So, but minus 1 not belongs to n. Okay, so this is the closure law, where the operands with the operator, if belongs to set yes, the resultant operand must also belong to same set of yes. Okay. Next comes is the associative law. There is an association between different operands with a operator. Which is the operator involved here is the multiplication operator. Okay. What does the associative law will say is, a binary operator star or multiplication operator on a set of yes is said to be associative. They can say that they are associative star when x into y into z is equal to x into y into z. Okay, you can write like this. X into y into z is equal to x into y into z. They are associated. Even though their expression is different, they are associated with binary operator star for all x and y and z belongs to S. That means operands must belong to same set. Okay. Along with that, you can have another expression, x plus y plus z. X plus y is an expression, plus z is another expression. This must be equal to x plus y plus z. See, here it is an expression. X plus y plus z is another expression. Here it is 1 and this is 2. They must be associative with each other with respect to multiplication operator and plus operator. Okay. So, you can say that the set or binary operator multiplication and addition operator will be associated with the elements of S even if the expression holds good. Okay. The next law is commutative law. Okay. So, here again commutative law is explained with the help of the multiplication operator. A binary operator multiplication said to be commutative with a set yes when it holds the expression x into y is equal to y into x. That means 2 into 3 is equal to 3 into 2. If they are equal, then it belongs to set of yes. If it belongs to set of yes, then the operands are commutative to each other. X plus y equal to y plus x. If you look at the previous example, previous law, if I check with that x, y, z, if you take it as 1, 2, 3, what does the associative law says? If 1 into 2 into 3 is equal to 1 into 2 into 3. Is it equal? 2 into 3, this is 1 into 6. So this will be equal, is it not? So even plus is fine. If you take minus operator, it may be 1 minus 2 minus 3, 1 minus 2 minus 3. What is the result now? 1 minus 2 is minus 1, minus 3. This is 1 minus of 1 will give you 1. 2 minus 3 minus 1 will give you minus plus 1. So this will be minus 4 and this is 2. That means the binary operator minus does not holds good the associative law with a set of yes. Because if this is set of natural numbers, this is not a natural number. So the operator minus will not hold good for associative law with the set S. Okay. Same with the commutative law. Most of the laws holds good for both the multiplication operator. Most of the operators will hold good for both the multiplication as well as the addition operator. Okay. This is 2 into 3, 3 into 2 equal to 6, which belong to same set. Okay. If you take plus 2 plus 3 is equal to 3 plus 2. Is it not? 5 equals 5. Again belongs to set of yes. Okay. If you take again minus operator, 2 minus 3, is it equal to 3 minus 2? 2 minus 3 will give you minus 1. 3 minus 2 will give you 1. Even though 1 belongs to set of natural numbers, minus 1 does not belong to set of natural numbers. Is it not? So commutative law on multiplication operator holds good only when x into y is equal to y into x for all x and y belongs to yes. Yes, it holds good for plus operator also. X plus y is equal to y plus x. Whenever there is a reverse, then it will be a commutative law. Okay. Next is the identity element or identity law. Okay. An identity element is said to a set S is said to have an identity element with respect to a binary operation multiplication on S if there exists an element E which belongs to S with the property that E into X generates the X and X into E also generate X. So what it says is there will be an identity element which can be applied on a binary operator, multiplication operator. That identity element belongs to set of natural numbers. Okay. When it is applied on binary operator, multiplication, it will give the same result of the operand x. Okay. If you take identity element as E, when you apply identity element E with the multiplication operand operator and an operand x, it will give you the result x. Okay. For every x belongs to S, which is the operator which gives the same result of x is, in case of multiplication operator, 1 is the identity element. Okay. 1 is the identity element in multiplication operator. How? If you take a natural number 5, if you multiply it with 1 and same x equals 5 multiplied with 1 will give the same value as x. Is it not? So 1 is the identity element in case of multiplication operator, whereas for addition operator 0 is the identity element. For plus operator 0 is the identity element. If you take a natural number 7 plus 0 is equal to 0 plus 7 is equal to 7 plus 0, which gives the same value 7. If you take x, 1 into x equals x into 1 is equal to x. For every x belongs to I is the set of whole numbers. Okay, any set you can take. Okay, the 0 is the identity element in case of plus operator, whereas 1 is the identity element in case of multiplication operator. Okay. Next comes is the inverse law or inverse element. Okay. What does the inverse law says is, a set having the identity element E, again comes the identity element E, with respect to the binary operator. Which operator? Any operator. You can have any operator. To have an inverse, can have an inverse whenever for every x belongs to S. If x is an operand, x belongs to set of S. There exists an element y, again which belongs to S, such that x into y gives you the identity element E. Okay. So what does the inverse says is, if you have an element x, you can have an inverse element y. When these x and inverse element y is multiplied, you will get the identity element E. Okay. So what does this says is, the operator plus over I with E equals 0. Okay. The inverse of an element A is minus A here. Since A plus minus A will be equal to 0. If I say 5, 0 is the identity element for plus operator. So plus operator has an identity element 0 and multiplication has an identity operator 1. Okay. Okay. If you take an example 5, okay, plus minus 5. Okay, when you give the reverse of 5, so this will give you the identity element 0. Is it not? So this is what the inverse says. Inverse of x will give you identity element E. Okay. Distributive law. What does the distributive law will say is, if dot operator and multiplication operator are two binary operators, if they are two binary operators on a set S, the multiplication operator is said to be distributive over period operator, dot operator, whenever x multiplication y dot operator z is equal to x into y dot x into z. Okay, like x into y dot z is equal to x into y into x into z. Okay. So this is distributed over the operands. Okay. So this is an expression. This is distributed now. X into y into x into z. Okay. Distributive law holds good for both these operators when this multiplication or this expression holds good. If you check 1, 2, 3 for x, y, z, 1 into 2 into 3 is equal to 1 into 2 into 1 into 3. Is it holds good? 2 into 3 is 6. 1 into 2 is 2 into 1 into 2 is 1 into 3 is 3. So 6 into 1 is 6. 2 into 3 is also 6. Okay. Distributive law holds good when this expression holds good. X into y into z is equal to x into y into x into z. Okay. Next we have the axiomatic definition of Boolean algebra. How do you perform the axiomatic operation on Boolean algebra using the plus operator and the dot operator? Okay. So there will be two values, 0 and 1. Okay. So we need to define the algebra for the binary values. Okay. So this Boolean algebra was developed by a scientist known as George Boole in the year 1854. Okay. Because of this person, the algebra which gets operated on binary values are called as the two operands that holds or that gets operated with the operators are called as Boolean values, and the algebra which uses these Boolean values are called Boolean algebra. Okay. So this Boolean set contains only two values, 0 and 1, and two binary operations, plus and multiplication or dot operator, addition operator and the dot operator. Okay. Now we need to have the axioms for closure law with respect to plus and dot operator, and identity element 0 for plus operator and 1 for dot operator. Dot can be termed as multiplication. Okay. Plus and the multiplication operator. We are not concentrating on the minus and the division because most of the laws doesn't hold good for minus and the subtraction operator and the division operator. So we concentrate on the addition operator and the multiplication operator. Okay. Commutativity holds good with respect to plus as well as multiplication, like x and y equals y plus x plus y equals y plus x into y equals y into x. Okay. When you check for distributivity law of multiplication over plus and plus over multiplication, you are combining these two. Now x into y plus z is equal to x into y plus x into z, and x plus y into z, both the expressions, is equal to x plus y into x plus z. If you take the example, okay, x into, say if you take 1, 2 plus 3 is equal to 1 into 2 plus 1 into 3, as we have discussed in the previous slide presentation. 1 into 6, it is 2 plus 3. Okay. Is it holding good? X into y, 1 into 2 plus 1 into 3. 1 into 2 is 2, 1 into 3 is 3, 2 plus 3 is equal to 5. But this does not hold good in normal mathematics, but holds good in Boolean values when you have only zeros and ones, that we will check later. Okay, when you check with the example, same 1 into 2 plus 3 is equal to 1 into 2 plus 1 into 3 will give you 1 into 5. This is 2 plus 3. So 5 into 1 is 5 and 2 plus 3 is again 5. This holds good for distributive law. When you take the inverse example, okay, you have complement of every element of x is x dash. With x plus x dash equals 1, inverse says you have to have the identity element. So, identity element of plus is 0, where you will get x plus x dash equals 1, then x into x dash equals 0. Okay. When you check with the binary values, x plus x dash 0 is, x is, if it is 0, x dash will be 1. So, this will give 0 plus 1 equals 1. Okay. Suppose x is 1, x dash is 0, again will give you 1. Okay. When you check for multiplication, if x is 1, x dash will be 0, will give you 0. If x is 0, x dash will be 1, reverse complement of x. Okay. Again will give you 0. Okay. So, this is how the postulates holds good for both the addition operator as well as the multiplication operator. Alright. A two-valued algebra is defined on a set of two elements. Okay, again we need two elements to operate the Boolean operators. Okay, so be 0, 1 and two binary operation plus and minus. So, rule of operations are and, or and not. And represents the multiplication operator, or operands the, or uses the plus operator, and not uses the complement. Okay, why it is and is using multiplication is, and represents the state of multiplication. Like Boolean values 0 and 1, we can have four combinations: 0, 0, 0, 1, 1, 0 and 1, 1. And operation, multiplication operation will give you the result 0, 0, 0, 1. That means and. When you apply and operation, the value will be true only when two statements are true. So, this is where the algebra holds good. When both the operands are 1, the result will be 1. Otherwise, the values will be 0. With respect to OR, we can have 0, 0, 0, 1, 1, 0, 1, 1. So, when you apply plus operator here, this will be 0, 1, 1, again 1. So, 1 plus 1 is 1. So, what does it say? If any one of the state 0 or 1, result will become 1. Okay, 0 or 1. If any one becomes true, either this or this, that is why it is called as the OR operation. Or either this or this. Either this must be 1 or this must be 1. Either this must be 1 or this must be 1. Result will become 1. Okay. When both is 1, both are 1, no problem. Obviously, it is 1. Is it not? Either or. Either this or this. If it becomes 1, the result will be 1. What does this say? 0 and 1. That means both must be 1. Then only result will become 1. Otherwise, it will be 0. And means both must be true. Both must be 1. Or is, if any one is 1, I am okay with that. You give the result 1. Whereas not operator is a single operator which applies on either 0 or 1. If it is 0, result will be 1. If it is 1, result will be 0. Okay. Here we have the tabulation of the AND operation. That is, x, y or the two operands. When you apply AND operation, that is x and y, 0 and 0 is equal to 0. If both the operators are 0 operands, then it will become 0. If one of the operand is 0, then also it becomes 0 because another one is not 1, not true. If one of it is false, the result will be false. If both are true or 1, then only the statement become 1. Okay. Next is OR operation. X plus y plus gives the same result as OR operation, OR. Anyone. So plus gives the same result as of OR. So OR represents or plus represents the OR operation. Dot operand represents the AND operation. You need to remember this operations throughout the subject. Okay. Remember again, dot operator represents the AND operation, or the multiplication operator represents the AND operation, whereas the addition operator represents the OR operation. Okay. Next comes is the NOT. NOT has only one operator, x. The resultant is x dash, complement of x. If x is 0, x dash is 1. If x is 1, x dash is 0. Alright. Next comes the closure law. Closure law is obvious with the binary values. 1, 0 belongs to set of B. Here B is set of two values 0, 1. Okay. Plus and multiplication both involve this operand. Result will give you only 0 or 1. As we see in the previous slide, it gives only the values which belong to set of B. Is it not? So closure will hold good. When you check for identity elements, okay, when you apply 1, you will get 0. When you use multiplication operator, you will get 1. Okay. Next is the commutative laws. X plus y equals y plus z. Okay. When you check with the tables, so this kind of table which holds the true values, either 0 or 1, both are true values. That is why it is called as the truth table. Okay. This kind of table which involves two values, 0 and 1, are usually called as the truth table because both will be true, either this or this. You can go there, you cannot go there. You can read, you cannot read. You can read, you cannot read. Like this. So this true statements will be represented as 0 and 1. It is called as the truth table. Okay. We use this term of truth table almost in every concept of our subject. So remember this terminologies. One is AND represents multiplication operation, which represented by dot operator, and OR operation represents plus operator. Okay. Along with this, these kinds of tables are called as the truth tables, which contains only the values 0 and 1. Okay. So when you check for the commutative law, whether it holds good for this, we shall apply the operation of x plus y. What you will get is x, y, you will get 0, 0, 0, 1, 1, 0, 1, 1. X plus y will give you 0, 1, 1, 1. Okay. If you go for y plus x, So this will give you 0, 1, 1, 1. That means x plus y is equal to y plus x, because values in truth table of both the expression is equal. Okay. If you check for x into y into x, so this will be x into y represents AND operation. X into y, what are the values x and y can have is 0, 0, 0, 1, 1, 0, 1, 1. X into y is 0, 0 into 1 is 0, 1 into 0 is 0, 1 into 1 is 0. Okay. If you take y into x, 0 into 0 is 0, 1 into 0 is 0, 0 into 1 is 0, 1 into 1 is 1. Okay. So x and y, 1 is 1. So x into y is equal to y into x with respect to truth table values. Okay. Both the values in truth table are equal. Okay. Next is the distributive law. Okay. So distributive law, what does it say is x into y plus z is equal to x into y plus x into z. Or you can check for x plus y into z is equal to x plus y into x plus z. You can check for both the expression. You can observe here, if you calculate these values, both the values are equal. Is it not? Values in both the truth table are equal. That is why it is called as the distributive law holds good. Next, if we check for complement, x plus x dash equals 1, that is 0 plus 0 dash, that is 0 plus 1, it is 1. Okay. If you take 1 as x, x dash will be 0, 1 plus 0 again is equal to 1. Same with the multiplication operator, x into x dash means 0 into 0 dash, that is 0 into 1 is equal to 0, whereas 1 into 1 dash is complement of 1 is 0. So, it will be 1 into 0 again equal to 0. Okay. So, there will be 3 operations: OR operation, AND operation and a NOT operation. Alright. For a set of 2 elements 0 and 1, you can have the OR operation, AND operation and the NOT operation. In the next session, I am going to explain you about basic theorems and properties of Boolean algebra. What are the different properties and theorems that are used in the Boolean algebra? Okay. Thank you.